Many of our viewers have been asking us how we've been able to directly record content from our older CGA and EGA systems during our first boot videos. It seems like it should be simple enough. Just go online and pick up a simple converter. The problem is, nobody makes those. So today, we're going to show you how we do it. Hey guys, it's Jacob with Tech Retrospective. Today we are going to be blending over 30 years of technology into a single-purpose rig to convert the old analog signals from our vintage systems, many of which are older than I am, into digital-coded, high-def content that we can route and record with our professional digital video equipment. Fortunately, or unfortunately, depending on your point of view, we're going to have to get a little bit technical, especially considering what a long time span we're trying to bridge to accomplish this seemingly simple task. To make things even crazier, we should really go back to the earliest days of broadcast television in order to help you fully understand what we're doing. Pictures and model numbers are nice, but not only does technology and availability change regularly, but there's also some possible issues with taking shortcuts and getting the wrong stuff for the job, as we discovered. If you're ready for the biggest time warp in Tech Retrospective history, here we go. Whoa! Production televisions began to appear in the late 1920s. Investments in infrastructure were a little slow during the Depression that followed, and after that came the big one, which took up everyone's time and resources. Before World War II, the television industry was an insane mess of different broadcast standards and television types. The technology inside your home TV set depended on where you lived and which company had their broadcast towers near you. To put things in perspective, imagine a modern world where you could only get Netflix in a given neighborhood. And if you happened to move into a new neighborhood that only had Amazon Prime, you had to buy a brand new 200-pound television and give your old one away. The important point here is that throughout the years, standards were developed such as the 525 line video broadcast format and the 4:3 aspect ratio. Fortunately for us, we can fast forward to the mid-1970s where the emerging home computer industry took to using NTSC and PAL standards when designing displays for home computer systems. Older video game consoles are probably the most familiar example of this strategy. It was not necessary to purchase a display for these consoles because one of the accessories inside the box would be an RF modulator, and/or a switch box allowing the user to transition between a broadcast signal from the antenna and the modulated signal from the game console. Dedicated computer monitors of the day often used an RGB connector, which was in the form of a single RCA plug. TVs containing this type of connector sometimes had an RF modulator built in. Sometimes the graphics adapters themselves handled RF modulation. When IBM released their first PC with CGA-based graphics in 1981, the RGB connector was the only option. While Hitachi had designed the video controller on IBM's original CGA adapter to output a variety of resolutions, not all of them could be transmitted using the RGB standard. In 1983, IBM released the 5153 display, which had a plug for TTL, or transistor-to-transistor logic. This TTL cable had the familiar 9-pin connector found on many of our vintage systems, and it allowed the video adapter to send an RGBI signal to the 5153. RGBI stands for red, green, blue, plus intensity. It was a combination of analog and digital channels that allowed the monitor to reproduce 16 colors. It's at this point in history that the NTSC and PAL broadcast standards were no longer up to the task of handling computer graphics, at least not to their full potential. Improvements to CGA came along, particularly in the form of EGA, or Enhanced Graphics Adapter, which offered better resolutions, more color options, and it did so while using the same D-sub 9 connector as CGA. This basic configuration would be the standard for PC graphics until the release of the PS2 in 1987. The PS2 had what's known as VGA, or Vector Graphics Array. VGA used a D-sub-15 connector, and in modern terms, this DE15 is able to transmit signals as demanding as 1080p. However, back in '87, the controllers and VRAM could only support 640 by 480 resolution. VGA was a significant step up from CGA or EGA because VGA could reproduce 256 colors. The signal was still composed of both analog and digital information. Together, these were known as RGB-HV, or red, green, blue, horizontal sync, vertical sync. The digital portion of the VGA signal was used to allow the display to communicate with the video adapter. Information about supported resolutions and refresh rates could be used to ensure the computer was displaying information correctly. It wasn't long before the industry realized the potential of RGB-HV. In 1988, NEC spearheaded the development of VESA, or Video Electronic Standards Association. The new VESA standards allowed for the creation of SVGA, which was basically VGA on steroids. SVGA supported resolutions up to 800 by 600. SVGA held its own until well into the 2000s. With high-speed memory prices dropping and so much of our video workload being handled by computers by the early 2000s, a new standard was needed. In the case of video, there are few, if any, advantages to analog signals. Enter the Digital Display Working Group. The DDWG invented the DVI standard, or Digital Video Interface. There were several versions of DVI, mostly designed to promote compatibility with SVGA devices at the time. HDMI came on the scene in 2003. HDMI, or High Definition Multimedia Interface, is electronically compatible with DVI by design. And in fact, HDMI is basically DVI with a channel for audio included. Eventually, HDMI 2.0 would support 4K resolutions at 60 FPS. SDI, or Serial Digital Interface, is a strictly professional standard for video transfer using coax and BNC connectors. It is far more flexible than consumer standards because it allows multiple channels of audio and video to be configured based on the specifications of the devices involved. Today, it's commonly categorized by the data transfer rates being used. Presently, the max is 12 gigabytes per second, or 12G SDI. 24G SDI is currently under development. In our studio, we generally only need to stream HD or 4K content with 2 channels of audio from a single device. This means 3G SDI is enough for our purposes. A video hub handles routing of signals digitally to and from all devices in our studio, including the monitor I'm reading the script off of right now. So how do we get from point A to point B? Here's a general rule to start with. Computer display standards are a combination of aspect ratio, display size, display resolution, color depth, and refresh rate. When converting video between different formats, all of these factors must be accounted for at every step of the process, something that we learned the hard way. In the case of something ancient like an old game console or an early computer system with an RCA RGB output that follows NTSC standards, we need to first convert it to a digital format. RGB is an analog signal, which means that an analog to digital converter can scan, sample, and digitize it even if the information doesn't make sense. The analog to digital converter might be programmed to screen garbage signals out though, so it can be helpful at times to have an old analog playback device on hand for those times when things aren't working and you get nothing but a black screen. With such a device, you can actually see the snow or bug fights, or whatever you choose to call the static, is famous on screen, like, in the movie Poltergeist, that stuff. Yeah. For our digitizing RGB, we're using a simple Rasfox HDMI converter. The only configuration we have to consider here is the selection of either 720i or 1080p for output. Either one would probably work for our purposes, since we have a scaler in the signal chain, more on that later, but we might as well keep everything the same and use 1080p. HDMI is designed to make use of standardized aspect ratios such as 4:3 or 16:9. In the case of our RGB output, the scaling process must include an aspect ratio change in order to prevent dark spaces on the sides of the 1080p picture. Another alternative might be to use up all of the horizontal real estate and chop the bottom of the picture off completely. Fortunately, our converter doesn't work that way. Audio can be introduced into the digitized signal in a couple of different ways. In the case of the Rasfox converter, left and right RCA inputs are present and can add the audio into the HDMI signal. We'll show you how we include it with CGA or VGA in a minute. In the case of a computer system using the DE9 TTL connector, things are slightly more complicated. Information about scan parameters and some other complicated technical wizardry are coded in the output signal from the computer's video controller. As we've said, standalone CGA to HDMI converters are non-existent, or nearly impossible to find unless you're good enough at electronics to modify a board designed to go into a new television and create your own enclosure, complete with other boards for whatever type of I/O you need. You may have noticed during our background summary that new digital video standards were willfully designed to be backwards compatible, at least electronically. This was done to make upgrades to older systems practical. It also works to our advantage because HDMI is similar to DVI, which is similar to VGA. Enter the MCE to VGA adapter, which is actually a kit that can be configured to perform a multitude of functions. In our case, we're using it to input the analog parts of the CGA signal and format the output based on the digital information encoded in the input signal. Scaling is not necessary at this stage because VGA, by design, supports all of the resolution and color depth of CGA. Aspect ratio, refresh rate, and screen size are also identical at this step. The device itself, as we've configured it, has the DE9 input on one side and the DE15 VGA output on the other. We're using a simple passive CGA splitter before the MCE2 VGA, so we can see what we're doing on an actual CGA monitor. Also, if problems occur during the conversion process, we can still see what the computer is doing. We have one more step to go before even getting to the same stage as the RGB to HDMI conversion I described earlier. We need a converter in the form of this Audio Authority VGA to HDMI converter scaler. This is also where we introduce any audio from the computer into the signal chain, since HDMI contains audio information and VGA does not. The physical setup for this is simple, but configuration must be done properly for it to work at all. Most of the problems we encountered while figuring this process out occurred at this stage. Unlike the RGB analog to HDMI conversion, if the VGA to HDMI converter doesn't properly read digital information from the VGA signal, it can't read any display information. The converter must be able to read and adapt to this information while also being able to convert the refresh rates from whatever the VGA output is running into whatever frame rate the next device in the chain is configured to run. When dealing with digital video formats, it is common for devices that display them to give the user options about the aspect ratio. In the consumer world, this usually takes the form of viewing modes like panorama, wide, or zoom. In our case, the aspect ratio is determined by the output format we've selected when configuring the Audio Authority converter. Color depth is also set during this analog to digital conversion. The RGBI signal from the DE15 VGA signal is scanned, and values are mapped digitally according to the specifications of the output format, which in our case is 1080p. Now comes the final step in the conversion part of the process. Whether originating from a RCA RGB source, a CGA graphics adapter, or VGA, we have converted the signal to full digital 1080p, being sent to our next stage using HDMI. This signal is sent to a device called the Decimator MD Cross V2, HDMI to SDI cross converter. The Decimator takes the HDMI signal and, if necessary, converts it to 1080p at 60 frames per second, which is what our video hub is set to use. The Decimator actually has several functions it can perform, but we are using it to code and format the SDI signal, as well as communicate the digital information to the hub. The hub does not perform any conversions or scaling. It is simply there to route the AV signal to one or more destinations of our choosing, such as the HyperDeck digital video recorders or one of several monitors. So looking at it from left to right, here is our converter to convert from composite video sources into HDMI. Very nice. Next to it is the MCE to VGA converter that we mentioned previously. This takes in our CGA signals or MDA or anything like that and converts it into a VGA signal. Next to that is our VGA to HDMI adapter. It's very cool that we were able to pick up one just like the really expensive one, just with different branding on it. And here is our decimator. That's what we use to transfer the signal from HDMI to SDI and send it off to be routed to any of our different monitors, like the one here behind me. And over at the end is a HDMI splitter in case we need to send an HDMI signal off to multiple locations. Really, this is a setup designed to be a jack of all trades. We still are missing a couple of inputs that we'd love to be able to convert. We're still working out how we're going to convert RF signals, for example, but I'm sure those will be added to the desk at some point. Even though we did as we have suggested earlier and considered all of the factors involved in video format conversion, saying we ran into a few snags would be an understatement. Remember when I explained that analog to digital conversion is an all or nothing proposition? To start with, we got a whole lot of nothing. This makes the diagnostic process very frustrating because when something in the process doesn't work, it's really hard to tell what part of the long chain is the issue. We were, however, able to develop what was supposed to be a long single chain of devices into two shorter chains. Both of these smaller chains worked independently but not together from start to finish. With this information, we were able to conclude that our first snag occurred at the VGA to HDMI conversion step. We could convert CGA to VGA and view it on a standard VGA monitor. We could send HDMI to the video hub, as we often do, and send it wherever we wanted. The problem was not with any settings. It was with the devices themselves. Specifically, it was a small and simple VGA to HDMI converter we were using. We followed our suspicions about the converter and replaced it with a different model. Still no success. So we tried yet another model. And as it turns out, the problem is that simple, low-cost converters work well when sending a signal to a modern consumer TV, but they don't have the color depth scanning and frame rate conversion capabilities required for our specific output requirements. We shelved the tiny little converter boxes and picked up a StarTech Coverage AV. which is nearly identical to our audio authority converter scaler. If you're following closely, you might be wondering why we didn't use it. We thought our frustration meter was maxed out, but we discovered that our eBay seller had included a power supply with the StarTech converter that fit perfectly into the AC connector, but supplied nearly 3 times the voltage required by the device. The results weren't as spectacular as fireworks as some of our computer's power supplies have had, but by the time our seller provided what he called the correct power supply, the damage had already been done. As it turned out, the replacement wasn't right either. Fortunately, we were able to find the Audio Authority VGA to HDMI converter scaler. It's pretty clear that it's a more substantial device than the little converter boxes we first tried. Even after solving that problem, switching between graphics modes has been confusing one of our converters, which prevents the video signal from getting to the recorders. We're still working through that particular issue, but it'll probably make an interesting follow-up video when we get a handle on it. Running operating systems that didn't exist when the computer hardware was manufactured can complicate matters, so it's likely that we'll have to familiarize ourselves with the specifics of OS versions in order to stabilize that process. Well, that's all for you guys today. I hope it was educational. There was so much to go through. Believe it or not, we actually cut this episode's length down. It was originally going to be over an hour long. We had so much more detail included in it, but that's a lot. So of course, if you have any questions about our setup or the specific details or any of that tech stuff, you can ask us in the comments below or on our Discord server, and we'd be happy to answer. Of course, if you have any recommendations on how we can improve our setup, we'd also love to hear that. And that's really all I have for you guys, so I'll see you next time.